I freeze at 14,000 feet, so.
Okay, sorry for the latency. Welcome to today's lecture. So yeah, today we're going to talk about, my friend Francisco suggested me this very peculiar name, wavelength discriminators, which means instruments that allow us to separate wavelengths. And today we're going to talk about the theoretical basics for Fabry-Perot filter. On Thursday we're going to talk about the theoretical basics for classical spectrographs. Then next week we're going to jump straight away to the polarimetry. And then I think the week after that we're going to talk something about the practical aspects of, well, we can say practical aspects of spectral polarimetry in general. Okay, so the idea today is to go through some theoretical basics, and these are maybe some of the things that you did in your optics classes, but we're going to try to go through them again and then discuss again how that relates to some things that we want to do when we are observing. So we discussed previously image formation, and basically when we talked about the image, we didn't pay much attention to the wavelength of the light, right? We assumed that it more or less comes from some region of the wavelengths, and of course we were not imaging in UV and infrared at the same time, and of course things couldn't apply identically to huge ranges of wavelengths, but we were not concerned about wavelength distribution of the light, right? But I said many times, and I'm going to say again, that different wavelengths sample different depths, and ideally what we would like somehow to get is to get 3D data cubes such as this IBIS data cube that we have seen a few times by now, which basically I'm showing now as image of one region of the sun, successively changing the wavelength that we are looking at. So basically this right panel here suggests that we are only looking at this very, very narrow wavelength range indicated by this moving red, let's say, distribution, okay? But another way to look at this is that what we want to have is that when we look at an image, we want to have a spectra, actually a spectrum of each pixel, right? If I now plotted individually from this data cube wavelength distribution and intensity for each pixel, you would have, I don't know how many, like 1,000 times 1,000, roughly. You would have 1 million spectra, which are strictly speaking all different, right? And we are very familiar with the spectra and some things that we can learn from that. And people started studying spectra basically as soon as they invented first spectrographs, which were nothing but a prism that was projecting the light on some sort of emulsion so that we could sort of figure out was the distribution there. And you are probably familiar with these efforts from more than 100 years ago of people to classify stars. And we talked very briefly about the fact that the differences here between the spectra are not because these stars are fundamentally different in their composition. They're there because they are fundamentally different in their temperature. And we can sort of do, and this is going to be a little bit of a leap, I'm going to make it a little bit more dramatic than it really is. But in a way, when we look at the sun, since we see it in this huge spatial resolution, it's as if we were looking at millions of stars simultaneously, because each pixel in our image has a different spectrum and somehow corresponds to a different atmosphere. So when we study the sun, that's what we want to do. We want to ascribe a specific atmosphere to each of the pixels. And you are all probably very familiar with huge, nice spectra of the sun as a star, such as this one here, which is really, really beautiful, and you can see all these spectral lines in detail. But of course, looking at these images and just nice colors with these dark stripes doesn't tell us a lot. What we need to do is we need to actually look at the numbers. And here I'm going to look at, so this is a very high resolution spectra, so we can really see nice details. And here we can see that the spectral lines actually are not delta functions. They're not just the absence of light. They have this very, I would say, sophisticated and intriguing structure there, right? So you can see that somehow very often, especially in these intro classes that we have in astrophysics, we are told that lines are roughly Gaussians and so on and so on, and there are many papers and a lot of research out there the 3 spectral lines as Gaussians, and sometimes that's true, right? But in the case of most of the very strong lines that are formed in the solar atmosphere, you see this very interesting shape here, right? And you would have a lot of trouble trying to describe this with a very simple function. So to truly understand the shape, in this case it's H alpha here, you really have to do a lot of modeling, and we're going to go through the theory of that modeling during the second part of our course. We can also look at the different spectral lines, and these are now sodium D1 and D2 lines. And now I'm plotting the same chunk of the spectrum as before. So we were looking at roughly 10 angstroms before, we are looking at 10 angstroms now, and you see now that these lines are, for example, deeper, right? Their cores are more, there is less intensity coming from there, they're more narrow, but then they're still broader than, for example, these lines here in the middle. And in these spectra, basically all the lines coming from our atmosphere are removed, so you're really looking at the spectral lines coming from the sun here. And it's really cool, right? Actually, I'm not sure whether the telluric lines are removed. Don't erase that. Yeah, but here there are no telluric lines. The interesting lines are the lines that are really created in the sun. So these two big sodium lines, left and right, and then in between we have iron and nickel lines, and so on. Okay, so from here you could already infer something, and people basically can use this sort of spectra of the sun as a start to, for example, infer the chemical composition of the sun, and so on and so on. But we want to go a step further. So you already know quite a bit about it, so why don't we very quickly hear what you think, what we can learn from the shapes of the spectral lines. Come.
Velocities, temperatures, magnetic fields.
Right? Okay, so these are all very far-reaching things, but what are some more, like for example, what would velocity be related to in first approximation? Like if you just look at the spectra without knowing in detail the physics behind, what you would look at just to roughly estimate the velocity.
The wavelength of the line core intensity.
Yeah, exactly. So the position of the minimum.
Yeah.
For example, if your spectral lines were asymmetric, what would that imply? Do you have any hunch?
The gradient in the velocity.
The gradients in the velocity, right? For example, then we know that, for example, if the line is stronger, it means that there is more absorbing material, right? Now, it's not going to be because the sun is inhomogeneous in its chemical composition. It's usually because the temperature is different, so material behaves in a different way. Sometimes we can see some lines that don't look at all like they look in the mean solar spectrum, right? For example, calcium 8542 is in the mean solar spectrum. It's a nice absorption line, but sometimes you will see it as almost emission line, or as almost flat line, like with very few features there, right? Then we can also look at the polarization, and we're going to talk about it next week. Yes, Tom?
Well, you have to be careful because composition changes with height in the solar atmosphere, like the flip effect. So if you start looking up in the corona, you're going to have different composition compared to the photosphere.
Very high, very high.
Yeah.
I think we are here talking about much more tame regions at the moment. But yes, I think technically you're right, although I'm far from expert on that. So maybe when we have Steve's lectures and we talk about what happens above the limb and stuff like that, maybe we can talk about
What is this event?
It's called the first ionization potential effect. It's like elements who have lower first ionization potential get accelerated predominantly in the solar wind. So basically in the corona, like it happens somewhere in the chromosphere. Yeah, when they're over abundant.
Okay.
Well, like a factor of 3 or something.
I see. So some elements from corona are easier to escape or harder to escape. So basically,
Yeah.
Okay. Well, that's a good thing to have in mind. But it's also something that we can maybe measure, right? If we have very detailed modeling. So yeah. So in principle, eventually, what we will want to fully understand what's happening here. Like we will want to say, okay, line looks like this, how do I engineer it back to get the temperature? And that's when we talk about inversions and so on. But in principle, now we just need to agree that we need to know the distribution of the intensity with wavelength as detailed as possible, right? We want to know all the details of our spectral line. And as I said multiple times, in principle, what it enables us to do is that we can look at the spectra of each pixel and we can prescribe or ascribe a model atmosphere to each pixel. And in a way, we could reconstruct the 3D structure of the solar atmosphere that way. So in a way, high spatial and spectral resolution spectroscopy or spectropolarimetry, if you want, when you fully make use of all the data you have, you are sort of performing some sort of tomography of the solar atmosphere. And the key part there is to have information in different valence. So what we're going to talk today is how to obtain the information at different valence. So as we said, the fundamental problem there is that the data cube that we want to obtain is a 3D cube. So it's information in X, Y, and lambda, right? But our detectors, they're 2D. So they can only store variation of intensity with two quantities, right? And maybe, and there are actually many ways how to unpack that 3D cube and put it on your 2D detector. But perhaps the most obvious one is just to employ some sort of filter, right? I can say, okay, from my specific monochrome, I'm just going to isolate one small valent region of my intensity, and I'm going to look at it, and then I'm going to change the wavelength. And then I'm going to look at the multiple wavelengths that way. And we are very familiar with that in the context of SDO, for example. And SDO routinely observes through multiple filters to obtain these amazing images of the sun at various UV valence. And you have probably heard many times that these different UV valence correspond to different physics or different temperatures in that context. But if you look at this image here, you will see that valence differ by a lot. So for example, we have these AIA images that basically invisible, and then going all the way down to 94 angstrom, right? So it's a huge span. Well, for example, when we look at our IBIS video before, we saw that, actually let's look at it again real quick. We saw that the valence here changes over a very small range, right? We have like, what is it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15 points over the range of 2 angstroms, right? And if you look at the core of the spectral line, it's very, very nicely and finely sampled. So the difference here between, I don't know, Kevin, do you remember how fine is the sampling in the line core?
Probably less than 100 milliangstroms.
So tens of milliangstroms, right? So this is something very, very fine. So today our goal is to figure out how the instrument that can separate this works, and the instrument that does this, and in the case of IBIS, for example, is Fabry-Perot interferometer. And here is another example of observations done with Fabry-Perot interferometer. This is a famous CRISP instrument in Swedish solar tower, and these are examples from a paper published by Milan Gosic. And I want you to look at this image very carefully and tell me what you see. So it's obviously image of the sun at few different wavelengths. Don't pay attention to the top right one. We will understand what the magnetogram is in a couple of lectures. Just look at the images. So here we have images at 3 different wavelengths. And if you look very carefully at the text here, you will see that these wavelengths are continuum of a neutral iron line, which basically samples the photosphere. Then the core of calcium 8542 line, which samples, let's say, lower chromosphere. And here is H alpha, which samples, let's say, typical chromosphere or something like that. We can discuss about that. But there is something else that I want you to pay attention to. Something else hidden in numbers here. So what else? There are valence, and there are also times, right? And each valence corresponds to different time, which is in a way pretty obvious, right? I can't simultaneously, I mean, in principle I could, but if I have one instrument and I tune it to different valence, I can't record these valence at the same time. So in a way, what we are doing here is we are spending some more time, some more observing time, in order to obtain valent information. And this might sound very trivial, but keep in mind that when you look at these images here, and in any of your images that you're going to obtain at DKIST with your filter graph instrument, image is created in one moment, but different wavelengths are created at different moments, right? So we are slicing our 3D cube in a way parallel to the XY, so we are slicing it wavelength at a time, and these wavelengths are now replaced by different moments in time, okay? Which in a way means that you need to take care about, and that we talked about it in some different contexts last time, you need to take care about how fast your physical, your scientific problem is evolving, right? If it's something that is happening on the scales of seconds, you shouldn't sample your wavelengths every 10 seconds because you're gonna see different things at different wavelengths, and we don't want that. We want to see one and the same phenomena at different wavelengths. But we're going to talk about it. We're going to talk about it further. But this is just to emphasize the fact that you always have to sacrifice something. So in this context, you are sort of sacrificing your time resolution to get the wavelength resolution. Okay. We will see that in the case of the spectrographs, we are sacrificing in a way both time and spatial information to get wavelength information. And in the case of integral field units, you would narrow down your field of view, but you would be able to preserve both the spectral and temporal resolution. And that is all shown in this maybe confusing image that we're going to unravel slowly as we go through this part of the course. And here there are a lot of instruments, and actually we have quite a few examples from DKIST, but for the moment we are focusing on the first example here. And in a way, these are the most intuitive for us, and these are filter graphs. So this is your original data cube that sun gives you in some context, and now you want to observe it, you want to sample it, you want to measure it. And one way to do it is you take this saw here and you cut it one wavelength at a time, and you obtain these nice slices here. Right? Yes.
Why is there a hammer on the other side? I can understand the saw. Cut something.
You're rearranging.
Because you need to break it.
You're beating things into.
Yeah, I'm not sure. Quick in San Francisco.
And this is cutting things up, slicing the
Yeah, I forget that part.
This is forcing the 3D cube into a 2D representation.
Yeah.
So it's implicitly
Yeah.
mixing spatial
Actually, there
aspects.
is if you wish, the left side is not fully consistent with your original image because you would have to have a sequence of those within your left side.
What do you mean?
Well, if your data is the top cube, you need multiple cubes at different times.
Yeah, that's what's illustrated here. So here you see, wait, I didn't understand, sorry.
You're starting from one data cube.
From one data.
What you have in the left bottom part of your diagram is multiple data cubes taken at different times.
Whereas
No, but they're not multiple cubes, they're multiple surfaces.
Well, but you have a T. That
because in time, as you
yeah,
build
but
the cube.
he's starting from data that is not taken at different times.
Correct.
Okay.
So here, when you take it and you take these different slices, you have different times for each slice.
Okay, it wasn't mine.
Oh, you're assuming the sun doesn't evolve in that way. Yes.
Yeah. So let's discuss this in a little bit further on. So what we basically want to do is we want to make an image at one very well defined wavelength, then change that wavelength arbitrarily to another value, do that again and again and again until we have enough data to answer our scientific problem, right? Whatever, I mean, we think that we're going to answer a scientific problem. There is interpretation coming later and writing the paper and convincing other people that you're correct and so on and so on. But that's another story. So basically, let's dissect a little bit more what we just talked about. So this is the cube here, which is in XY lambda, and then as you separate it in lambda, you are, and this is illustrated here on the right hand side, on the right part of the graph, is that you're replacing in a way lambda information. I mean, you're not replacing, you're mixing your lambda information with time information because all these different wavelengths are obtained in different time, right? But still, somehow, this is something that is most intuitive to us, right? If I have an image and I want to get wavelength information, the easiest thing for me is just come up with an instrument that isolates one wavelength and find a way to change that wavelength. And luckily there is an instrument like that, and it was invented a long time ago, I think end of 19th century or something like that, and that's Fabry-Perot interferometer. And Fabry-Perot interferometer, and here you get the chance to enjoy my amazing, my terrible handwriting once again. Fabry-Perot is basically nothing but a slab that is capable of transmitting some amount of light and reflecting the rest. Right. So what happens here, and let's dissect this image very slowly, you might remember this from your undergrad studies, is you have a plain, nice, plain monochromatic harmonic wave coming from the left side, and it's characterized by some incoming electric field, and part of that electric field is transmitted, part is reflected back. Then from the transmitted part is transmitted again, and it exits the filter, part is reflected back, where again, part is transmitted backward, but then there is another reflection, and part of that is eventually going to be transmitted forward. So as you repeat this mental exercise here many times, what happens here is that you have, strictly speaking, infinite amount of beams that are propagating, and they're all coherent because they are all the consequence of the original electric field here. So they can interfere. And always keep in mind what interference or superposition is. We always can, when we have coherent waves, we add the electric field. When we have incoherent waves, we add the intensity. Good. Yeah, go ahead. Okay, if somebody just had the mic turned on. So now let's see how these beams that are coming out are interfering here. And now there is a little bit of math here, but it's always interesting to go through this. So the first, or let's call it here, zeroth beam that goes through, it has the same phase as the original one, except it's attenuated by this factor here, TT prime, which are basically coefficients of transmission between this, let's say, outside medium and the inside medium, and between the inside medium and the outside. Okay, then the second beam has additional factor of R squared, which comes from two reflections. So these R and T are some numbers that are smaller than 1, okay? They have to be, okay? But then there is also a phase difference that comes from the different path, right? So take a look here. The first beam is just going through with respect to, or zeroth beam, with respect to the zeroth beam, first beam made 1, 2 paths through the filter, okay? So the physical path of that is 2 times d, where d is the thickness of the filter, but then I also need to multiply that with n, which is index of refraction for the medium filter is made of. We can always assume it's, I mean always, we can roughly assume it's 1, because in principle it can be 1, we just need the reflections inside. And then finally k, which is the wave number, right? Because we always get the phase, which is dimensionless. And then you move on, and actually what you will see is that each subsequent beam has an extra term of R squared and extra 2D and K phase lag with respect to the original one. And when you add them all together and make use of the fact that they're basically a geometrical series, you're going to get something like this here. You're going to get this term 1 over 1 minus R squared e to the I delta. And this delta is going to be an important quantity. This is basically a phase lag due to 2 reflections. That's the phase difference between 2 consecutive beams, right? What we have here on the right. And now we can calculate the intensity from the electric field just by multiplying it with its complex conjugate and taking 1/2, which corresponds to the temporal averaging. And through some math that you can go through if you don't remember this and you want to fully understand how the Fabry-Perot functions, you will get in the end that the ratio between the transmitted intensity and the incoming intensity looks something like this. So it's 1 over 1 plus, then this term depending on big R, and now big R is just the square of small r, And basically, in a way, you can understand it in a way that small r gives you the fraction of reflected electric field. Capital R gives you the fraction of reflected intensity. So you can derive the capital R from the. Was there a question? No, okay, very good. So you're going to get something like this. And there are some of these, super cool exercises where you remember how you derive sine, cosine from all these exponential things. Yeah, and so on and so on. So this is the important relationship here. So we will see that the ratio between the transmitted and incoming intensity depends on the phase difference between the two consecutive beams and on the reflection coefficient of your filter. And this phase difference between the two consecutive beams depends on, let's remember what? Index of refraction of your filter, thickness of your filter, and the wavelength you're looking at. Okay. So now, as one of the examples that you probably studied when you were in school is that you had rays coming in different angles. We now, for the simplicity, implicitly assume that the angle is basically 0, but there is an additional term of cosine theta, if you really want to be pedantic, and that would in principle tell you that transmittance varies with this incident angle, and in one way, if you looked at one wavelength, you would get the interference pattern like this. So if you took Fabry-Perot and the laser, and arrange them with some auxiliary lenses and something like that, you would get the interference pattern like this. And then if you took these equations and made an example, you would actually get interference pattern that really looks like the image that we saw before. Don't pay attention to these angles here. I think I messed something up. But you would really get this, you would get this central minima and then periodic maxima with angles going outside. But this is not what we want. We want something else. And I found this amazing picture that illustrates what we want. And this picture tells you what happens when we put few different wavelengths in our Fabry-Perot instrument. So obviously you can see now that minima and maxima have different positions for different wavelengths. And that of course makes sense because the position of the maxima and minima are going to depend on the values of this delta, which is the phase difference, and the phase difference for fixed thickness depends both on the angle of the incidence as well as on the wavelength. So what are we going to do now is we're going to fix the angle of the incidence, and we're just going to focus on different wavelengths, right? So, but before we do that, let's dissect the main equations that govern the behavior of our Fabry-Perot once again. So we're going to define this auxiliary quantity f here, which we call coefficient of finesse, and that's, or fineness. I mean, I don't know. I just assumed it's finesse, but maybe it's finesse. It's finesse. Okay, nice. And that depends exclusively on the reflectivity of your mirrors. And then the ratio between the transmitted and intensity and transmitted intensity is, sorry, transmitted and incident intensity is going to be something like this. 1 over 1 plus f sine squared. This should be delta half. Sorry for that. I'll fix it when I upload the slides. Where delta is something like this up here. So it depends, as we said, on the angle, index of refraction, thickness, and wavelength. So now what I'm going to assume for the moment is I'm just going to assume that everything except wavelength is fixed. Okay. But before that, let's just look at another plot where I'm, for simplicity, going to plot the transmitted intensity, or let's say the ratio between the transmitted and incident intensity, which I'm only going to call transmittance from now on. I'm just going to plot it for some arbitrary values of arbitrary grid of deltas, right? So forget now about the angles, valence, and so on, for few different reflectivities here. And this tells you that more reflecting your filter is, these transmission maxima are more narrow and better defined. So in a way, it's in our best interest, you're probably already guessing this, to have as reflecting mirrors as possible in order to have very well defined maxima here. However, don't forget that more narrow maxima are better defined, but they also let less light go through. Okay, so eventually you're gonna have to, and you will have that as one of the homework problems, to actually discuss this and try to figure out optimal ideal filter graph for your scientific problem. Yeah, but this is just one thing. And also, like if you really have poor mirror, so you see here for R equals 0.5, you never reach zero transmittance, right? So even your contrast between your maximum and minimum transmittance is poor. Okay, cool. So now let's plot, and this is something that you can try, and I will share the Jupyter notebook with you to reproduce these results. Let's now plot transmittance versus wavelength. So what I did here is I made a very, and actually as you can see here, it's a very it's very small span of wavelengths. So I took plus minus 0.1 nanometers, centered at 500 nanometers, and I made a Fabry-Perot which has thickness of 1 centimeter, reflectance of 0.9, and index of refraction 1. And then when you plot transmittance versus wavelength, it looks like this. Okay. So here we see a problem. We can't really isolate one wavelength only. So this now behaves more as a comb in some way than really as a filter. Okay. We're going to talk about later a little bit about the ways how to handle that. So obviously you're already guessing that you can stack few different filters and then you can isolate exactly what you want to see. But now let's look at the two things that we are interested in. But before that, what exactly am I measuring? So now imagine that you have a filter which behaves like this. Okay, and all that we derived so far was some ideal wave of one wavelength and so on. But now I'm talking, let's imagine what would happen if we had a spectra, which is the distribution over all wavelengths. So obviously some wavelengths would be transmitted completely, some would be basically completely absorbed. So what am I finally going to measure? Can somebody tell?
Integral or whatever.
Exactly, the integral of the product between the filter and the incoming intensity. So keep in mind that we are always only measuring counts, right? So strictly speaking, if you were just to take this, complicated distribution of the transmittance and use that as a filter, what you would get is you would get the product of your original intensity times your filter integrated over all wavelengths, right? So and literally this is the mathematical definition of a filter. Right? That's something that you put inside of the integral to isolate a region of the function that you're interested in. So obviously our ideal filter in this context would be a delta function. Because the delta function isolates exactly what you want. Of course we cannot get that, right, Mama?
But then you can't measure it.
So you can't measure it because then it's also super narrow. Right. Yeah, but I just gave you this integral here to stress what we want. So we want very narrow function t, which is basically centered on only one location. Cool. And in that context, we need to talk about two properties of a Fabry-Perot filter, and these are the spectral resolution, which is basically connected to the width of these maxima here, and something called free spectral range, which is basically the distance between the two peaks in a filter.
Sometimes the separate peaks are also called orders.
Or orders, yeah.
People will encounter that.
Exactly. Yeah. So if you hear the name order, and we also hear the name order in spectrographs.
Right, because one peak is 3,000 wavelengths.
Yeah.
Right, and then the next one is 3,000.
3,001 wavelength.
3,002.
Yeah.
Right, that's how many.
Yeah. So yeah, we're actually going to go to that. So what I was thinking now is, keep in mind that we have completely analytically described this function. So this function is given by this set of equations here. What I did basically is I fixed the numbers for n, d, cosine theta. I chose a grid of lambdas and I plotted this thing here in the middle, right? So let's take, okay, maybe not 5, maybe 5 is too much. Let's take, where was it? Let's take a few minutes and think on our own with some pen and paper how you would derive the expression for free spectral range of the Fabry-Perot. So what we want is we want to given lambda central or characteristic lambda and d and so on. Let's try and derive what is the distance in wavelength between these two peaks here, right? And for that you'll have to make use of these equations here. So I'm going to leave these equations hanging here, and you take a few minutes. Yes, Momo?
Oh, sorry, I might have missed it. Did you mention why when you make the cavity that you were talking about, you make it between two glass plates? Because in your derivation, you just show the cavity, right? And you're like, oh, you just have the interference there. But why do you make the air cavity between two glass plates? Is it just to get like the high reflectance of the
Instead of,
So parallel.
need something to hold the coating. You need a cavity between two reflective surfaces.
Sure, but then why don't you use just like one piece of glass that has like very high reflectance on both sides?
Oh, well, have you gotten to that? Yeah. What? That, yes, that is actually the formal definition of an etalon.
Mm-hmm.
An etalon is an interferometer with a fixed spacing.
Oh wait, but you're never gonna get that code.
We're going to get to that. Okay, we're going to get to that. Yeah, okay. So now we are still talking about some ideal slab, but we're going to see then how we change the things that we want to change.
Okay.
So let's just try.
Etalons.
So basically what we are looking at is we are looking at the separation between two maxima at the given wavelength, right? So you can now try, and everything is fixed except lambda. Right? So your f is fixed, everything is fixed. So this here is delta half. I'm sorry about it. So just imagine, I could probably draw it on the screen for the Colorado students. Yes. So assume that you are at one maximum, which is, for example, roughly at 500 nanometers. And then you are looking at the next one and try to find the separation between them. So once again, because I'm already starting to lose it, it should be f psi squared delta half, not delta. I didn't proofread this very carefully when I programming here. But you have it, for example, in this derivation here, right? 4r over 1 minus r squared is f. So you get sine squared delta half. Right? You don't have to carry it all the way, just an idea will be enough. Okay, so let's go on. Let's look at the solution. So we were talking about what we are measuring here and so on. So let's try and derive this so-called free spectral range. So basically, what we want to have is we want to look at the places where the transmission is maximum, right? And the transmission is obviously maximum for the cases when sine of delta half is 0, right? Which means the difference between two consecutive values of delta half should be 1 pi, right? Which means the difference between two consecutive values of delta should be 2 pi, which is also somehow intuitive, right? If I increase the phase difference by exactly 2 pi, then nothing should change, right? And then what we're going to do is we're going to write this delta, which is 2 pi, as d delta over d lambda times, there should be partial derivatives here, but doesn't matter, times delta lambda, okay? And then you just substitute the expression for delta, which is 4 pi n d over lambda, so it's going to be 4 pi n d over lambda squared. I can neglect 0. 0 just tells me that as I increase delta, my lambda has to decrease, right? Times this delta lambda FSR, which is basically the definition of our free spectral range. And then when you derive from there what delta lambda FSR is, it's going to be lambda squared over 2nd, which means the thicker echelon you have, or the thicker filter you have, the more dense these maxima are. Okay, now in a similar way, we can derive the, yes, Niraj?
What happened to the cosine theta previously?
Well, we assume that for this filter that we are making, we are keeping theta fixed, right? So then the easiest thing is just to say cosine theta is 1, which means that light is incident on our filter. But it actually tells you about a very interesting trick that people sometimes do, is that when they want to change the wavelength of the maximum transmittance, they rotate the filter a little bit, right? Because cosine theta will then interact with the other stuff. So now, in the same way, we can derive the spectral resolution. So in a very similar way, I'll just go back to the plot that we said, okay, if I want my 2 point sources to be separable, I need them to be separated basically roughly by this quantity here, which is some characteristic width of a spatial PSF. We can define the same thing in the context of wavelengths, right? I can say if I want to separate two wavelengths very well, I need to have such and such wavelength resolution. Or simply said in another way, this wavelength resolution will tell me how narrow range of wavelengths I'm isolating from my original intensity distribution, from my observed spectrum. And I want it as narrow. If I'm interested in very, very fine details, I want this to be as narrow as possible. So we're going to do very similar things. So we're going to start by saying, okay, my characteristic width is the width where the transmitted intensity falls to 1/2, right? So my, 1 over 1 plus f sine squared delta half is 1/2, which implies from some very simple considerations that my delta 1/2, which is half width at half maximum, should basically be 2 times 1 over square root of f, assuming that the angles are small, okay? And then my full width, or actually just width at the half maximum, is going to be 4 over square root of f, in radians. And now how do we translate that to wavelength? Well, we will use the same trick. We will say that gamma is d delta over d lambda times delta lambda, and I'm going to derive delta lambda from there. And it's going to turn out that delta lambda is, again, lambda squared over square root of f pi n d. And now there is a very interesting consequence of that, is if we look at the ratio between the free spectral range and the spectral resolution is going to be proportional to the square root of f and nothing else, right? So even the nd and lambda squared are all going to cancel between these two things. So for given, I mean ideally looking for the given filter, once I make it, once I choose the reflectance of my filter, I have these things fixed, right? And I can try to make it thicker, and it will make, you know, it will make the maxima thinner, right? I mean more narrow, which you can see from here, but it's not going to make it more packed, right? So we are sort of encountering the problem here, and we are seeing how important it is to have good reflectance, because the bigger reflectance is going to result in bigger f, is going to result in more separated maxima with respect to their width. Okay? So for another exercise, oh no, I wanted to hide this from you, but we can do it together, and you can just make sure that I didn't make any mistake. We can try and calculate the so-called spectral resolution, and this is now the first time that we are defining spectral resolution. And the spectral resolution is the ratio between the reference wavelength that you're looking at and the wavelength range that you can resolve. And in the context of Fabry-Perot, this wavelength range is the thickness of our mask. And you can see that when you combine these, the expression for delta lambda for the spectral resolution in your wavelength units, and the lambda is going to look something like this. So now if I substitute some reasonable quantities here, so if you take reflectance of 0.9, which is not terribly much, you would get square root of f equal to roughly 60. And then you substitute the other values. Here I chose my index of refraction to be roughly 1. I chose the thickness of my filter to be roughly 1 centimeter, which I think should be the thickness of VTF. I think it says, yeah, roughly. Then you divide it with the wavelength, you're going to get this relatively big number here, which is like 4 times 10 to the 5, which is rather big spectral resolution, which means that the ratio between my reference resolution and my smallest step, actually not smallest step, my smallest resolvable wavelength distance is basically 500,000, right? Then we're going to compare that, in the next class we're going to compare it with spectrographs and so on and so on. The actual spectral resolutions that we work in terms of Fabry-Perot, I think, are usually a little bit lower than this. Actually are not much lower than this.
And this,
Yeah.
but they're a factor of 2 lower, at least. And, yeah, now more than that, factor 4. I mean, there's a lot of other reasons the profile gets broadened.
Yeah.
And so the reflectivity isn't enough to define the resolution in a real Fabry-Perot. So that's why.
I guess it also depends on how much light we're absorbing and so on.
Yeah, there's all the errors and things,
Sure.
and the optical effects.
Yeah.
To broaden the profile.
You mean how defined the surfaces are and so on?
Right. And and just the optics of you're mixing multiple beams going through.
Yeah.
So that.
Sure.
So,
Okay, but this is the ideal case. So when we do, actually the best thing, of course, is that when you have your instrument is you should have somehow measured or estimated the shape of the transmission, and then you can use it in your calculations, but this is like the most ideal possible case that happens there. Okay, cool. So now let's finally see what we want to do, because now we want to look at the different wavelength, right? And the thing that we can change there, and what Momo hastily wanted to ask us previously, is that now how do we look at different wavelengths? And the answer is we can devise our filter in such a way that we can change the distance between two reflecting surfaces. And that is why you actually don't have one slab of material, and if we had one slab of material, it would be called etalon, and it would be called etalon because etalon is like a reference for something, right? And it's only allowing this one reference wavelength, or this reference set of wavelengths, while if we make our filter to instead of being like just one slab, being basically two walls that can finally be tuned between, with respect to each other, then you can change your thickness a little bit, and that way you can change the wavelength, the maximum transmittance of the filter. And you can do the same exercise as before. So we can now see, given this, resolving power, gamma here, how much do I need to change the thickness of the atolon to move my wavelength by this amount? And actually, for the example that we had before, we got that it's something like 2.5 nanometers, right? While our, state-of-the-art filters that we use today can do it in much, much finer steps. So something like 1 angstrom. So you can tune the separation between these two reflective surfaces down to 1 angstrom precision. And we are not talking now about the wavelength of the light. We are talking about physical distance in the laboratory in your instrument of 1 angstrom. So Kevin made sure that I don't forget to tell you this, because it's actually super impressive that we can tune something to 1 angstrom precision in physical space, right? Okay, super cool, right? And actually, if you go, I just went, because this morning I was looking around the web pages and so on, so I went to the web page of ETF at the Kippenheuer Institute for Solar Physics, and then they say that their precision is exactly something like that, 0.1 nanometer, 1 angstrom. Okay, so let's summarize some of the properties that we have here, and let's discuss a little bit what happens here and what we need to always have in mind. So basically, the Fabry-Perot allows us to do something that was intuitively our first wish, right? To have images obtained at one specific wavelength. Okay, and of course we can't really do it at one specific wavelength, but we can make very narrow distribution and isolate all the other ones and just look at, almost one specific wavelength. And in a way, as I said before, it's as if we were slicing our cube in parallel in lambda space, so parallel to x and y. Right? And here, like the theoretical background of this is the multibeam interference. So we have these beams that are reflecting a sign coming out and then interfering, and the ones that are constructively interfering are being allowed to go outside. And if we have good reflectance and as we heard in general, good quality, which means a lot of not very high level of small imperfections and so on, we will have very well defined maxima, but always keep in mind that will mean that less photons will pass through your instrument, right? Because you can't allow more than 1. You can't have transmittance which is more than 1. So, and you're always measuring this integral, which is the product of your incoming intensity and your field, okay? And in practice, we can avoid these other maxima because I have shown you that even on a very small range of wavelengths, you're going to have a lot of maxima. And you can get rid of these by making multiple, basically successive Fabry-Perot instruments that allow you to isolate, which are slightly different. So only one maxima is transmitted through both of them, while the other ones are canceling. Because when you have two filters, you're behaving as one filter equal to the products of these two. And you can also obtain it by using something called pre-filter, which is a more simple filter that we put in front of everything else, right? And there are also, you always hear this one challenge is how good Fabry-Perots are very expensive and so on and hard to make. And the main reason for that is that we now are looking only at one beam, but in principle what we have is we have many beams corresponding to many points in the sky, right, coming in and interfering. And they're going to enter our etolon or our filter at different places, but they all need to behave the same, which means that the properties of our filter need to be constant over the whole filter, which means that these two surfaces need to be super parallel to each other, right? And I never thought about this, so I thought like, wow, why are they saying that, I don't know, 25 centimeters filter is so, because I think that's the size of ETF, 25 centimeters is so big. But then actually when you think that you need to have two surfaces of 25 centimeters aligned to this 1 angstrom, then it's a really hard thing. And there are probably many other, engineering and technical things that need to be, that I don't know, and that we need to think about when we are talking. Very important thing that I want to stress is that it's very nice property of these instruments that you can choose which wavelengths to look at. Like they don't need to be uniformly separated, and you can literally say, okay, I want to look at the line chord, then very close to line chord, then very close to line chord, but now I'm not interested about this region, so I will skip these wavelengths, and so on and so on. So you can invent any basically wavelength sampling that you want. And in principle, if you really wanted, you could even jump in irregular regions. You could go line chord, then right, then left, then right again, then left again, and so on and so on. And there are actually some relatively interesting papers that deal with optimal ways how to sample something when you're looking at very dynamic processes in the sun in order to get good coverage. And we will see next time that when we look at the spectrograph, this is not the case. So spectrograph disperses your light, and what you get is roughly uniform sampling in wavelengths. Okay. And it's interesting in one way because you can observe a lot of wavelengths at the same time, but it doesn't allow you this kind of flexibility. And in principle, the image that you are seeing is exactly the image that you would see if there was no filter, except there was only one wavelength isolated. So all of the image is recorded in one moment of time. So when you look at one wavelength, you're looking at one moment of time. And then again, we'll see that with spectrographs, it's not the same because they work on a completely different principle. One thing that we'll also discuss more on Thursday is that the distribution of the transmittance with the wavelength is much more winged in the case of Fabry-Perot, and actually you can see that maybe here.
Much more what?
The wings are more pronounced in a way that in a way when you look at the intensity, when it comes to the small values, it needs more time to completely follow. Which can be sometimes, because in a way, and we have seen this from this interval before, that this instrument is also mixing your wavelength information from different wavelengths, right? If you tune into the line core, you are transmitting line core the most, but you are also allowing some nearby wavelengths to enter your instrument. Which means that, in principle, when you look, and this is also true for the spectrographs, of course, but maybe to a lesser extent, when you look at the line core, it's also going to have some contributors from the surrounding intensities. In principle, all your lines that you look are always going to be more shallow, yeah, and a little bit more broad than the original ones.
That's because you have all these successive interfering beams, right? So you have, right, both the spectrograph, the grading spectrograph, and the Fabry-Perot, you have a bunch of beams that interfere. With the spectrograph, you just reflect it off, and each beam is phase delayed off the mirror because of the grading. The Fabry-Perot, it's reflecting in there, and each beam that reflects and comes out is a little bit fainter than the previous one.
Yeah.
A little bit of light's been absorbed, some's gone through, and so you're not reflecting, the interference is now not between a set of equal beams, but
slightly,
each one is slightly reduced in intensity, so you don't get as good of a destructive interference away from the peak.
Yeah, that's actually a very good way to look at it.
And so that's why they're fundamentally different, the shape of the two.
Yeah.
Whereas with the grading, it's perfect.
With the grading,
You get perfect
can take the
cancellation in the
perfect
zero.
cancellations.
Here you can never get perfect cancellation.
Yeah, that's I didn't think about it that way. Yeah. Anyway, and actually we can take we're going to look at some data now, and we can see what comes out. So where were we? We were looking at the.
Can I make a comment?
Yes, absolutely.
So the properties of each interferometer depends on those three things, like the N, the D, and the R. And you can play with them depending on what kind of problems you have. The N, the index of refraction, can be changed too if you have something like Momo was discussing. If you have, there exists the Fabry-Perot solid state Fabry-Perot that use a crystal instead of having a glass or substrate with a coating painting on. And so, and there you change slightly the index of refraction, by changing the voltage at which this thing is kept.
Mhm.
So it's something, for example, the IMAX uses a solid solid state you need fairly high tensions of the order of 1,000. No, I don't remember. Thousands of volts. 1,000 volts. So they are delicate from some other engineering point of view, but they exist.
Yeah, but there are no moving parts.
You've
so
seen them
just-
break.
I've seen them. Right, there is no moving parts in that. And so in a sense, it's easier because you don't have to, I mean, once you've made the very clean parallel cavity, you know, these two parallel faces, you don't change that anymore. There is no problem of moving it and maintaining it. It's there. But yes, they can break
Yeah.
more easily.
Yeah, and actually, one interesting thing that I didn't mention is that, I mean, of course, not important for us, but essentially lasers are Fabry-Perot atoms, right? Each laser is put inside of one of these, and you first obtain the population inversion, and you obtain the amplification of radiation, but then you isolate these very narrow and coherent rays by having these reflective things. These two reflective surfaces that only allow very, very well-defined beam of light to go out. And actually, in some lasers, you can see the multiple maxima because the inherent emission of the gas is much broader than one maxima, so it can encompass multiple maxima.
You can calculate for your laser if you have, in a classical laser, I don't know the solid state lasers now, but in a classical laser, you know, you have a foot long kind of tube so it has a, you know, that's the width of your cavity.
Yeah.
And you can put another cavity inside and you get a single mode of that, the broader distribution.
Yeah, and in lasers you also have these transverse modes and so on, but this is also like interesting if you want to. Momo, do you have a question?
Yes, so when you have this surface coating, it's just I'm kind of resting my EM. It's like when you have a high reflectance, doesn't this mean that you're going to have high reflectance on the incident beam as well, or they're completely incorrelated with each other? Because you have light that's coming into the instrument, right?
Mm-hmm.
So when you have on the other side some sort of a coating that's reflecting on the other side, isn't it going to be reflecting on this side as well? Not really.
I mean, is the reflectance same from both directions?
Yeah, how are they related?
Like between the medium 1 and medium 2 and medium 2 and medium 1?
It is, basically it is, but because you have the cavity, any wave, another way to think of it is any wave of the right wavelength to get through the cavity will get through the coating on its original intake, right? As it originally is incident on the coating. In some sense it knows that it's...
No, but what I think Momo meant was the following one. I think actually
Why doesn't it
you're right.
reflect as it comes in?
Yeah.
Because the cavity is the right length to let it out. On the other side.
But on the initial incidence, you're going to remove like a lot of the light.
99.1%.
Except for the wavelengths where it will be transmitted.
So you're saying that if the wavelength of incident light is resonant with the cavity, that it essentially doesn't see the reflective coating at all?
Yeah.
How?
No, it doesn't make any sense.
But how do you
No,
know?
I know it doesn't make any sense, but that's how it works. Because you can actually see here that
It's like,
you're talking about this term, right?
No.
Because, well, this is the term that you were talking about, because what we had is that your original outgoing one hit is attenuated by this TT prime.
Yes.
And your argument is that the higher R is, the smaller this T needs to be, right?
Because the sun is one.
But keep in mind that this is valid for the electric fields. So electric fields are not added as the intensities, right?
Oh, I see.
So it's going to be different. And then as you carry out this completely, this term TT prime squared is going to cancel with something, and you are literally going to get this what Karen is saying. So for a proper resonant wavelength, they're just going to go through.
Wow.
that's right.
So you're saying that even though the electric field is greatly diminished in strength for even the resonant wavelengths, that the intensity won't be diminished for that resonant wavelength?
No, well, maybe the first beam's electric field is greatly diminished, right? But I'm strictly speaking summing infinite beams. And when I sum them all, this term T prime is exactly going to be offset by the appropriate reflections that appear here. And I'm going to get all the intensity coming through.
I call shenanigans.
Because they all didn't really destructively interfere at the first one, and such that at the first reflection it's like very small.
Yes.
Wow.
Right, then it's meeting all these things out of phase, right? I don't know.
So it's not the photon like knows how long the
Oh.
thing is before it hits it.
Oh, so okay, so I think all right, I think I get it now.
Okay, we can take a look at this further, but keep in mind that when you talk about the electric field, situation is much more complicated, right? I can in principle, electric fields are going to behave different than intensities.
That hurts my brain.
Right? It's a bit tricky, right? Because also the phase is important, the phase is changing and so on and so on. So, right? I can always write nothing as the sum of two electric fields with shifted phases and so on. So also the fact that I have the reflectance that is bouncing from the more optically thin, more high refractive index and changes phase. So that also plays a role and so on and so on. I can dig up this derivation from E&M basics, which describes this relationship between the reflectance and transmittance indices, and then we can see exactly how this goes through. Because I just relied here on this relationship between E and R, right? And I said from EM because I also remember that it appears somewhere, but I don't remember where. But I'll take a look and I'll let you know.
No, just because like if R is like 0.9 something.
Hey, but that's a big R, right?
But you want a big R, right? Here.
No, but that's big, that's capital R. It says it's the one that relates to the intensities. So it's going to be more complicated. Simply like when you think about electric fields, because these, strictly speaking, are actually complex quantities, right? Yes. These are because they correspond to electric fields. They also change phases of waves. So it's not going to be as easy as thinking, one half gets absorbed, but one half gets transmitted, so my maximum outgoing intensity needs to be 1/2. It's more complicated than that, right? Because, as I said, I could have, like, for example, electric field coming in, and then in terms of amplitude of the transmitted one being larger, actually, right? But then the reflected one has the opposite phase and so on. I'm just like hand waving, but in principle, when you talk about the electric fields, you need to think about the phase as well as the amplitude. Okay. So that's also hiding in these terms here, and I'll look exactly in the derivation, and I'll find this and let you know what happens. Okay. But also keep in mind there is this bouncing, and in principle, what we see is we can't really see this. It's not like the beam is really bouncing in time back and forth. You see the superposition of the electric field that goes out and the superposition of the electric field that's reflected. And when you have the resonance, the superposition is such that everything goes through, right? And nothing goes outside. When it's not the resonance, it's the opposite. Everything is reflected, nothing is transmitted. And there is a accompanying set of equations that correspond to the reflected electric field that is sort of, in a way, complementary to the transmitted one. Okay, so now this was super interesting, and I'm really happy that we discussed this, but let's just go very quickly over some famous instruments. And I wanted us to take a look at the data, but we can do it during the hands-on session in a couple of weeks. So basically every well-known solar telescope has a filter gravity instrument. So we know we spoke about the IMAX at sunrise. which is, as we actually know that it's a solid one. Then we have IBIS at VST, which is actually double ettalon, which means we have two Fabry-Perot instruments that are used there to increase the free spectral range. Then TESOS at VTT is actually triple ettalon, so you have three Fabry-Perots, and Francisco, who will give a talk next week about his instrument, their instrument, tested it at TESOS mostly. Then at SST you have these two well-known instruments, CRISP and CHROMIS, where I think CHROMIS is mostly for the very blue valence, right? CRISP is there, and it's relatively new. CRISP is there for a lot of time. And actually, I just learned this morning, I totally forgot that, for example, another filter graph, which is very well known, which is for HMI, is not Fabry-Perot, and is actually Michelson interferometer, which is, and basically in a way that's like a Fourier, right?
Right. So that has, yeah.
It's like a Fourier spectrometer, which is another very interesting concept, which we can hopefully, I will try to fit it just on one slide on Thursday, just to see how that works, where basically what you're measuring is the Fourier transformation of your spectrum using Michelson interferometer. And also for the DKIST, we're gonna see we're gonna have the so-called VTF, which means visible tunable filter. And yeah, as we will talk next week about the polarimetry, it's always good to have in mind that in principle, very often when we talk about the instruments, like for example, we say that IBIS is imaging spectral polarimeter, but in principle, the polarimetry part can be detached. So if somebody made their own polarimeter, they could come and attach it next to the ettalons instead of the existing one, and so on. So of course, in practice, I don't know how it works, and I don't know how feasible that is, but you could combine like your polarimetry and your wavelength discrimination are two separate processes, at least in ideal case. So, and we're going to see next week how we do that. Okay, I wanted us to look at some data, but we'll leave that for the hands-on. So, are there any more questions? Okay, I think we had a very good discussion. So this was just to see how basically this instrument works. And so on Thursday we're going to talk about completely different kind of observations. We're going to talk about the classical spectroscopy using so-called slit, and then we'll see what are some different approaches. I mean, what is the different approach? How the diffraction grading looks like? What is the spectral resolution of that? We're also going to derive it in a similar fashion as this. And we'll see that there is a fundamental difference there, that we are now trading one spatial coordinate for the valent coordinate instead of literally changing valence. Okay, cool, thank you. And just an announcement, we'll also probably start 5 minutes later, because there will also be a brown bag talk next week that that probably most of the people in Boulder will attend. So let's say it will roughly start at 2:05. Or something like that. Okay. Yeah, I will upload the slides and the video as soon as possible. So see you on Thursday, and stay warm.